Hello and welcome to video 2.4 where we're going to introduce the binomial and geometric probability models. So we've only talked about so far sort of like one sort of set model, the normal curve, the normal model, but there are at least another half a dozen, I think, that we're going to talk about in terms of probability models in the rest of the year. And so the next two sort of on our list are the binomial and the geometric probability models. And I'm introducing them together because they are similar-ish, but there is one sort of main difference between the two that we're going to try to highlight so that way you get really good at knowing which setting we're in and like what language you should be looking for and how that maybe affects how we calculate things. So to get us started, we are going to do something inspired by my son who loves Pokemon. And I have no idea if anything I'm saying here is legitimate, so just go along with it as I just made this up. So let's say you're a collector of Pokemon cards. So you buy packs of them regularly, and some of the packs contain these holographic cards. My son calls them the shiny cards. And so you really want those. And let's say we also know that from the official Pokemon website, they say only 30% of all the decks contain a holographic card. So here's sort of two questions that sound similar, but are different and that sort of put us into the different buckets of binomial versus geometric. So here's a binomial situation. A question that we can ask that would be binomial is, what is the probability that when you buy 5 packs, that one of them will contain a holographic card? On the other side there, something that is geometric, a question might be like, what is the probability that the 5th pack you buy is the first one to contain a holographic card? So I'd like you to think about what is the difference that you notice between these two situations? So I'm going to focus in on binomial first. So hopefully you sort of have an idea. If not, feel free to pause right now. But I'm going to focus in on that binomial. What I notice about the binomial is that we're focused in on a set number of packs. A set number of packs that we wonder about. In this case, we wonder, like, what's the chance that one of those 5 packs that I have in front of me contains a holographic card? That's a bit different than what I'm reading over in geometric. With geometric, what I'm reading is that there really isn't like a set number. We're more interested in, we wonder when we first get a holographic card. So I don't really have a set number in front of me in that scenario, what I'm reading. It's sort of like I grab 1, I open, I grab 2, I open, do, and then until the 5th pack I open. Yay, I have in here a holographic card, yay. While in the other one, I already have all 5 sort of in front of me, and I'm wondering what's the probability just one of these has it. It's not about the 5th one necessarily. The order there isn't as important as it is with that geometric setting where it's really all determined on like bust, 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 success. So that kind of changes how we would sort of calculate these probabilities. Because that first one with the binomial, what we're really thinking about is like, what's the probability that we have 1 holographic card and 4 non-holographic cards? And in that scenario, there's actually 5 different ways that you can do that, right? Like you can sort of think about how it's like, oh, well, I could get the first pack has a holographic card, and then I have 4 that don't, or I can have the second pack be where it is, or the third pack, and so on and so forth. So there's 5 different ways for me to get a holographic card from 5 packs. So when I go to calculate that, I'll be thinking about like, well, there's 5 ways to do it, and it's the probability I get a holographic card times the probability I don't get a holographic card. And so that would be 5 times 0.7, 0.3 times 0.7. Oh, sorry, I messed this up. That happens 4 times. So to the 4th power there, which is some number. I think I calculated it out earlier. I think it's about 0.07203, I believe. So like a 7% chance that if I grab 5, that I'm going to have a holographic card in one of those 5. But geometric's a bit different here, because in geometric, that order sort of matters. It's coming in on the 5th card, so the probability that the 5th deck has a holographic card, well, in that case, I'm going like, well, that's a no holographic card, followed by another no, followed by another no, followed by another no, and then that last one is when I get the holographic card. So that actually is kind of part of our, that's the scenario that would have been if I continued working on this here. That would have been the 5th scenario here, where it's like no, 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 yes, finally on the 5th one. So this binomial probability I have up here is part of, like that, it contains this example here. So what would that be? That would be 4 no's in a row finished up with a yes, which, oh, I just realized that is actually 0.07203. I was looking at the wrong place. This is a much higher probability. This is going to be 0.36015. There we go. Yeah, 5 times the amounts of what we just did there. So this is a 7. Sorry, that's very ugly. So there you have it. So that's the main difference there, is that in binomial, you sort of have what we'll call the number of trials sort of set from the beginning. And in geometric, there isn't a set number. You're just pulling until you get what you want. So that's the main difference there. So let's talk about language and our vocab here. So what we're discussing here right now are all examples of things called Bernoulli Trials. Bernoulli was a dude. Might have been 2 dudes. Might have been like brothers. I don't know. Anyways, Bernoulli Trials are trials that meet 3 conditions. The first is that what you're dealing with is binary. There's only 2 possibilities. There's success and there's failure. And you can turn a lot of situations where you're like, hold on, there's more than 2 possible outcomes. Like I roll a die, there's 6 outcomes, right? Well, you can change that to binary by just going like, well, I'm rolling a die, I'm gonna say 3 is a success and everything else is a failure. And that now becomes binary. So we're going to do a lot of that, where we get to take sort of things and just focus in on this particular outcome and anything else is failure. The second thing is that we need independence. Which we haven't talked a lot about independence yet, but we're going to get into that in our Monday probability lessons. For right now, what you're sort of thinking about is that each individual pull is independent from the others. The probability doesn't change. So like with the Pokemon cards, it's like just because you pull a pack out from the distribution and open it up, that 30% success rate isn't changing on you at all. And that brings us to the last one, which is it needs to be a constant success rate. So we need constant success probability for this. So again, that's where the independence can come into play here, is that without replacements, yeah, I guess sometimes our probability should change a little bit, but we're going to think about there's millions of packs of cards, so pulling 1 doesn't mean it affects the probability at all. So there's some notation here. We use the capital N for a normal curve, and so for binomial, we shorthand it by writing binom N, comma, P. What is N and P? We'll write that down below. N is the number of trials, and P is going to be our probability of success. So in the previous example, we were dealing in the setting of binom of 5, 1, 5, 1, 5 trials, 1 success, 5 packs, 1 of them containing a holographic card. For geometric, we're going to go ahead and talk about it as geom, and then there's just one parameter there, P, the probability P. That's the only thing that we need to worry about here. And you can then ask tons of questions. So I asked specifically above sort of, what's the chance of pulling it on for the first time on the 5th pack there, but I could have used the exact same model to ask about the 2nd pack, the 12th pack. Like this works for anything. So our model before was geometric 0.3. Oh, I think I said earlier that this P right here was 1. It's not, it's 0.3, sorry. Okay, so let's go ahead and take a look at some of these here. And we're gonna have you pause the video to read through each of these to see what you think. And then I'll give you a little nudge after each one to sort of help you think about it. So hopefully you've had a little time to think about it. As a little nudge here, so 2 of them are geometric and 2 of them are binomial. So make sure you go back through, if you thought there was like 3 and 1, it's 2 and 2, and try to remember which one is which and why that makes sense. Because in class, you're gonna come in and talk about these 4 with your team. All right, so we're gonna get back into the conditions. So we're gonna find ourselves knee-deep in conditions a lot, especially during the 2nd semester. And so we're gonna sort of talk a little bit about how these conditions help us out here. So the conditions from before, binary, independence, constant success probability. And I kind of want to go through and talk about like what's the reason or the details, the clarifications as to why we have these things. So let's do that really quickly. So why do we need to think about it as binary? Well, for me, the reason I think binary makes sense is it simplifies the situation a lot. If there's only 2 possibilities, that really helps out with your probabilities. Because, as we said, like P is the probability of success. If there's only one other scenario, then 1 minus P is the probability of failure. Those are supposed to be probability. I guess I'll write that above. And that's really helpful. Like I don't have to think about the probability of a success and then all these other probabilities of failures. I can boil it down to just like, oh, cool. I don't even have to use a new variable to talk about the probability of a failure. I can still use P. Introducing new variables will just complicate things. This helps to keep it nice and succinct. So independence. One of the things we're going to start finding out is that one of the ways we can claim independence is that we must sample less than 10% of the population. That's going to be a common way to sort of do that. So why is that going to be important? Well, if you're sampling a small proportion of your population without replacements, you don't have to worry about the probabilities adjusting so much. So think back to our probability last on Monday, where we did an example with cards, a deck of cards. And so in there, we're dealing with 52 cards. Well, if you pull 1 card out of that, okay, that's still less than 5% or 10% of the population. So the probabilities don't change a ton. But if you can imagine, I ask you, oh, hey, why don't you pull out like 10 cards? Well then, and without replacement, that's going to affect things. So like as you're going along, like you're pulling out and I'm keep asking you, what's the probability the next one's red? What's the probability the next one's red? And as you're looking at them, if you're getting a lot of reds, by the time you get to like the 8th card, like the probability that you pull a red has probably changed pretty drastically if you have a bunch of reds already out in front of you. It's 50% on the first pull, but if you grab 1, it's like, that's still kind of 50%. But if you grab like 6, then now the chances of grabbing a red is much less than 50%. So if it's a huge population, like on that same exact day, we talked about cats and dogs in US households. If you're talking hundreds of millions, then grabbing 50 doesn't really change things. Even if it turns out you grabbed a bunch of people that only own dogs, ultimately it's not going to affect the probabilities as much. So that's what we're looking for here. And that leads us into this last one here, constant success probability. So if there's a constant success probability, notes, that is also meaning that we have a constant failure probability because of that binary from above. And what it also does, it ensures a single model for any number of trials. We don't have to worry about, when we're going back here, this P in here changing after each individual poll from the population. So this is really helpful, is that we get to look at it and go like, hey, I said in the beginning it's geometric, with a probability of 0.2, and I can poll twice, 3, 4, 5, 6, 100 times, and every single time, that is still the model I'll be using. So let's go ahead and dig into some last problems here. So these last ones here, what we're going to do is we are going to read through them. We're going to decide whether it is geometric or it is binomial. And then we're going to check that those conditions work. The check that we have binary and independence and a constant probability of success here. So let's read through this first one and decide what it is. So a local fast food restaurant's running a draw a 3, get it free lunch promotion. After each customer orders, a touchscreen displays the message, press here to win a free lunch. A computer program then simulates one card being drawn from a well-shuffled standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. All 12 members on a school's choir place individual orders at the restaurant. What is the probability that exactly 2 of them will win a free lunch? So think about that for a moment. Is this geometric or is this binomial, and how do you know? So hopefully you decided on that this is binomial. So what you'll want to do now is think about how many trials and what's the probability of success here, and then go through and check each of the conditions, okay? So hopefully now that you've got that done, let's look at the second one. Lawrence likes to shoot a bow and arrow in his free time. A little weird, Lawrence, but you do you. On any shot, he has about 10% chance of hitting the bullseye. As a challenge one day, Lawrence decides to keep shooting until he gets a bullseye. What's the probability it takes him 20 shots until he hits the bullseye? I don't know why that says we hits. I guess he is Gollum. So what is that one going to be? Geometric or binomial? How do you know? So hopefully you landed on this is geometric. So again, we only need one parameter here, so that's going to be the probability of success, and then take a moment to actually then come up with all the conditions. Note, I don't want you to actually find the probabilities of either one unless you want to, not required for class. So hopefully now you've got a better understanding of the difference between binomial and geometric. If after looking at these two, you've realized that maybe you wrote down some wrong ideas for A through D on the front side, go on back. And next class when we get in, we're talking these 4 situations and your explanations. And I'm loving to hear sort of what are the parameters for these two? What are the conditions? How do you know that they've been met? So that said, we'll see you in class.